Today I will be speaking about this seismic hazard of India. That is this probabilistic seismic hazard map of our India, which is a new thing which we are going to introduce in our IS codes. So as if we have seen, right, this seminar has been going on for the past 4 days. So we had the first day, the lecture by Professor C.V.R. Murthy. So he has given a nice lecture on describing, the past, present, and future of our, the Indian seismic codes. And he also shown you this displacement based design concept also, which is going to come up in our future IS codes. And I think in the next lecture, Professor Rupin, he has expanded, and he has explained these concepts, in a nice fashion. Then I think yesterday, Professor Jaya from Anna University, she has given nice, things about this RCC. She has shown the design detailing, for earthquake things in RCC structures. So today my lecture will be on this seismic hazard map, that is essentially on the seismic zones and then this Z values. So now, as many of you may be knowing, in our IS 1893, we have one committee known as the PSHA Maps Committee, so which is responsible for this seismic zone map and then this Z values. So now, of course, this revision of our seismic zone map started almost 10 years back, but because of so many issues, it got delayed. And I think last year, this work has been taken up in an active manner. And the methodology, how to get the seismic zone map and other things have been frozen. They have been established, and the preliminary results also we have got for the seismic zone map, and maybe some fine tuning is required here and there. So maybe in another 1 or 2 years it may come on our IS code. So today in my lecture I will be showing you the methodology what we have adopted to get this new zone map, and then this new the Z values I will be sharing you in this lecture. Then as Professor CVR mentioned, so displacement based design is going to be using our future IS codes. So we have already started working on this displacement based design. That is the inputs required for displacement based design. That is the displacement response spectra. So I will be showing you these results also. Then peak ground velocity, which is very important for energy based design, CVR mentioned in this lecture also. So this also I will show you some of these issues. And then some more interesting things I will show you in this lecture. One is this vertical ground motion. See, generally in earthquake engineering, everybody thinks earthquake is only horizontal. So vertical is neglected.
I will be showing you the results also.
Then I will be discussing vertical spectra also, how good they are, how that also I am going to show you. Then finally, I will talk about this near field ground motion, which is a new thing. Of course, it is very well established in research, but in the design, how to design structures, and you will find out some new challenges, which come up when you are designing, the structures very close to the fault. So some of these issues I will cover up in my lecture. So this is the overall view are the topics which I'm going to cover in this lecture. So now to start with, all of this is the seismic zone map. Everybody, definitely would have seen in IS 1893 or in Google. If you just type, you will get this map. So everybody knows that our country has been divided into some 4 zones actually, starting from 2, 3, 4, and 5. And the Z values also they are here, starting from 0.1 G, and the highest value is the 0.36 G given in our IS code. And now here, if we show this map to any practicing engineer, actually, okay, and ask his opinion, he will say that these values are too high, followed. Right? We can't design. There are so many issues are there, and like that, that is their opinion. Now, if you ask any earthquake engineering expert, I mean, expert means a person who has worked in this area for the last 5 to 10 years. So they will see that they will say that these values are on the lower side actually. So many experts feel that we are under designing, underestimating these Z values. The reason is as follows. So like I'm showing you here the seismic hazard map of United States. That is official map of USA. It is available in the that USGS website also. If you see these values here, that is the Z values. They call as a peak ground acceleration, peak horizontal acceleration. So you can see the highest value is 1.6 G actually. Okay, in this region, and even in the Central Eastern United States, which is same as our South India, that is our peninsular India, the values are extremely high, as you see, 1 times gravity actually. So the US, the maximum Z value is, you see, 1.6 G. They have reported in their for their building code. Now, similarly, this is the map for Canada. So this also is available in Google, and you can download from NRC website. So here also, if you see this color coding here, so you can see the highest Z value they recommend is almost up to 3 times gravity actually. So which is 8 to 9 times what we are recommending in our IS code. And similarly, if you see, this is an Italian, the seismic hazard map of which is available in Italian website. Of course, Italy gives, not 2,500, they give for 475 years, which is nothing but, if you want to compare with our IS codes, it is Z by 2. So the highest PJ is something around is a 0.3 G, which means if you want to compare with our IS code, you multiply by 2. So the highest Z value that reported in Italy is something around 0.6 times, the gravity, which is almost 1.5 or 1.6 times higher than our IS codes. So when you look at all these maps, and now if you see our neighboring countries actually, okay, like Pakistan, Nepal, and Thailand, recently, they have done a lot of hazard analysis and they have reported their maps. So Pakistan, if you can see the Z value they have reported is something, it varies from 1 to 1.6 G. And now if you see in Nepal also, the Z values, the maximum value is something around 1 times gravity actually. Now if you see Thailand, which is towards our northeastern side of our India, so here also if you see the maximum value is something around 0.8 G. So now if you compare these values with our IS code, so obviously see we get a feeling that somewhere you see our numbers are on the, the lower side itself. So, and then apart from this, now most of you may be knowing that is yes, triple yes actually, that is site specific spectra. Okay. So nowadays these are mandatory, many clients are asking, suppose if you're building a tall building, so more than 25 stories or 30 stories. So generally people ask, whether have you done the site specific spectra or not. So what our code says, you have to do the site specific spectra also, compare with the IS recommended spectra, whichever is higher, you should use it in the design actually. So now if you're building a bridge span, if it is more than 100 meters, and if you're building any power plant, say thermal or nuclear or any power plant also, so you have to do the site specific spectra. Then for port structures, important structures like hospitals, airports also nowadays, and heritage structures also. So the clients are asking, to obtain the site specific spectra. Now here also we can obtain the site specific spectra from hazard approaches. But when you try to compare with our IS code also, we have some small, some issues are there actually in comparing these two. And nowadays, many of you may be knowing that is HVRA, that is Hazard Vulnerability Risk Assessment Studies, which are sponsored by disaster management authorities. So everybody is asking, like if there is going to be, and some 8 magnitude or 7 magnitude earthquakes, what will be the economic loss, for this state? Like recently, Tamil Nadu government also has started. They were asking, like you see, for Chennai, Coimbatore, and other cities to get these type of maps actually. That is what HVRA maps. Now to do all this work, you require, the seismic hazard approaches, and the seismic zone maps, which can be directly used in calculating, all these issues. And now most of you knowing that is a performance-based design nowadays is very popular. So if you want to design a structure as per performance-based design, say, so performance-based design, they don't want one Z value. They want some 4 Z values actually. So they want a Z value for frequent, then occasional, then rare, and then very rare. And these are defined in terms of the written periods like 43 years, 72 years, 475 years, and the 970 years actually. So you have to provide some 4 Z values for all these written periods. Then you can do this performance-based design. Now with the existing IS code, we can't do this performance-based design also. So now to handle many things. So now in 2009, a committee was formed by BIS as well as this NDMA, that's National Disaster Management Authority. So now so this was a working committee group, consisting of all these BIS people. Then the project team was led by me, and then this SERC, which is on the backside of our IIT Madras. So we jointly brought out this report on this PSHA map of India. So now this report is available online in this NDMA website also. So many things, the approaches, how to do the seismic hazard map was detailed, discussed in this report. and this report was sent to BAS also, but there was some fine tuning was required. So now, so this work we have taken up, and now we have revised this entire report, and maybe this year, we will finalize our new report also. So I'm going to show you from our, I am going to show you all the results, new results which we have got now. But all of you can download this report from this NDMA website. I'm listing here this, the HTML, that is a website link also, or you can type it in Google. You can download this entire report itself. So now to begin our seismic hazard, you should know some basics. Most of you know. I'm just recap kind of a thing. So now if you see what's an earthquake basically, so all of you know. I think other speakers also have told you. So that basically the earthquake is basically defined as, you see, a sudden movement of the ground that releases, you see, the elastic energy stored in the rocks, and it generates, these seismic waves. So once this ground movement starts, so seismic waves comes, and then you see the ground starts the vibrating. So you can see from this is a small animation. So you can see here there is a crack you can see between these rocks, and there is a nearby house. So when an earthquake occurs, so suddenly this the rock starts moving actually. So now here this is the most important thing is how much fast these rocks moves during the earthquake. So now I have mentioned here, so generally the rupture speed is around 2 to 3 kilometers per second actually. So you can just imagine 2 to 3 kilometers in a second means it is extremely, you see, very fast actually. So when things moves, very fast, what happens is the medium also doesn't know what to do. It starts, you see, a shaking kind of thing. It is same thing like our human also, like when we are going, when we met with some accidents or sudden changes, so we also start to see the vibrating kind of thing. So same thing happens to Earth. So when things are moving so fast, say, so automatically this generates using the seismic waves. And now here one more important thing you can see here. Now if you can see this red one, that is after the end of an earthquake, you can see these rocks, you can see like a plastic kind of thing. They can't go back to their original position. You will see something like a permanent offset here, which is known as a permanent ground residual displacement, or in seismological terms, say this term is known as, you see, the fling actually. And now this is a very, very dangerous thing in the near field region. Just imagine this house was located here, then nobody can design, you see, one column this side, one column this side. So it's very difficult to design structures located on top of the faults itself. So now this is how the waves starts propagating. So now the whole why earthquakes, the whole thing is, the most important thing is this rupture speed. If things was moving very slowly, say like you see 1 meter per second, or very slow, then no need to worry about these earthquakes at all, because you will not have any vibration, and it could have been fine. So whole these earthquakes becomes dangerous because only due to the speed actually. So speed kills this in earthquakes also. So this is how the waves propagate, and then you see the ground starts vibrating actually. So please all of you note down this most important thing, that is this fling, that is what we call as permanent ground residual displacement at the end of this earthquake. And now, as all of you know, this all the plate boundaries, everything now, this subject is very well established, and all the details are available. So now in the whole world, they say something around 43 plates are there, or maybe microplates. They're saying some 100 microplates are there, are approximately broadly some 40, 41 plates, you see, are there on our Earth. So now if you see this India, say, so we have a plate boundary, in the Himalayas and the Northeast. So that is considered as a plate boundary in our country. So now this is a story of our India. So as all of you know, India was, you see, a part of that Africa or something, and then we diverged Africa, and then we moved towards Asia. So the Indian plate velocity was 16 centimeter per year when it started moving from Africa actually. But after colliding with Asia, so now its movement velocity has decreased. So the velocity is around 5 centimeters per year actually. So now here I just want to make out the most important thing is, as I already told you, for earthquakes, the rupture speed is something around 2 kilometers per second actually. But whereas the Indian plate velocity is 5 centimeters per year actually. Okay, so you can compare these two. So the India, which is moving 5 centimeters per year, so generally finally causes an earthquake where the rupture speed is around 3 kilometers per second actually. Okay, so this is the contrasting things between the plate velocity and then using the rupture speed. And now, as all of you know, this is our story. Like India was there, Asia was here. So this collusion started, and of course, you see, the Himalayas was born, and everybody knows this these stories. And now this is how the Himalaya, if you take a section, say, you can see, because of this compression, the compression and you see this collusion, many cracks have been formed. So these are the most important faults, like main frontal thrust, then main boundary thrust, and main central thrust. So these are very important, the faults which have been formed in the Himalayas, and these are very active faults, and they are capable of producing, you see, a very great earthquakes, you see, more than 8 itself. And now, because in whole Indian plate is under compression, say, so almost all the faults in Himalayas which are parallel to Himalayas, all are compressive type of faults. So now in seismological literature, they call these as reverse faults also. And now most of you knowing these intraplate earthquakes also, these are very important for our South India. So now the earthquakes which occur in Himalaya, we call them as interplate, and earthquakes which occur in the plate, inside the plate, we call them as, you see, the intraplate earthquakes also. So generally, they say that the whole Indian plate is under stress. So 80% of the stress gets released near the plate boundary, and the remaining 20%, it gets released inside the plate, and it gets released wherever there are weak zones are there actually. Okay. So you can, if you take the whole India catalog also, and if you measure intraplate, interplate, you can see something like 80% on interplate and 20% on this side also. And now, so I have shown you the how earthquakes occurs, rupture speed. So the most important thing is all of you should know is the rupture speed is 2 to 3 kilometers per second, and then the Indian plate velocity is 5 centimeter per year actually. Okay. So now what happens exactly during an earthquake? So I'm just showing you some small ground motion simulation. So this animation has been done based on a numerical simulation for 2011 Sikkim earthquake. So you can see the Sikkim earthquake. You see it started here. So now you can see that there is a time here. So almost in 6 seconds, you see it has reached China. And you see in another 10 seconds, it has reached Iran, then Korea. If also the waves propagate that much faster actually. So now, if you put up an instrument, say, so like suppose in Gangtok, which is very near to the earthquake, if you put up an instrument and if you try to record, so the record looks like this. So you can see here the displacement. So the displacement, because things are moving so fast, say, so displacement, you see, it oscillates, this vibration comes up, and you can see in around 35 to 40 seconds, so the whole vibration is over in the near field. So now generally when things are moving so fast actually, so now we compute it's a derivative. So that is nothing but, you see, the velocity. And since we compute the derivative of velocity also, that is what we call as, you see, the accelerations. So now these how, you see, if you put up an instrument, you can record this. The ground motion looks like this: acceleration, velocity, and then this displacement. So now here I'm showing you the accelegrams for our Sikkim earthquake. So now when you look at these accelegrams, you see, we will not be able to make out anything from the accelegrams. The only thing is, you see, they are all increasing. They start from 0, they increase, and then go back to 0 actually. But now to get a physical meaning, say, if you plot their Fourier amplitude spectra or the power spectral density, which I'm showing here, you can see this graph here, which is a function of frequency here, and this is amplitude. So you can see all the earthquakes, they have energy from 0 to 25 hertz actually. But basically, most of the energy is concentrated from 0 to 10 hertz itself. In this range only, you can see, you see the full energy getting released from 0 to 10 hertz. Now, so here our civil engineering, you see the relationship between our structural engineering and earthquakes comes into picture actually. See, all of you know, this is just a thumb rule, widely used in practice. If you want to find out natural frequency of any building, say, if you know the number of stories actually, so 1 by 0.1 into n will give you the natural. It's like approximate kind of a formula. So if you have a 10-story building, say, so its natural frequency is, you see, 1 hertz. If you have single-story building, the natural frequency is around 10 hertz actually. So now, and most of our engineering structures, the bridges, the whatever structures we have, all our engineering structures, our frequencies lies from 0.1 to 10 hertz actually. So now you can see earthquakes also has energy from, you see, 0.1 to 10 hertz itself. So now, so earthquakes also, they have frequencies from 0.1 to 10, and our engineering structures is also from 0.1 to 10. So what happens when our structural things and earthquake things, both of them are same, then automatically the resonance comes, and the things gets amplified, and finally it leads to damage actually. So this is a relationship why a civil engineer has to study earthquake engineering, because of this problem. Suppose if earthquake frequencies were not in 0.1 to 10 hertz, if they are in some other range, then we don't need to worry about this earthquakes at all actually in our design. And now some of these concepts are very well established. It was known earlier also, and effects was also known. Now, if you see, the craze for earthquakes, this earthquake engineering has increased, you see, a lot nowadays actually. So everybody is talking about earthquake engineering. See, when I was doing PhD in 2000, when I started at that time, very few people was working in earthquakes. But now, when everybody is working about earthquake engineering, and a lot of popularity has increased, there is a scientific reason, you see, for this aspect. Like here I'm showing you, the deaths, generally the insurance companies are there, so they calculate, they are more worried about, this deaths, because the premiums and other things they have settled up. So now these insurance companies have calculated, say, like for example, when in 1897 there was one great earthquake in Assam. Magnitude was something around 8.1 to 8.3. So this earthquake, then the reported deaths was something around 1,500 people died during this earthquake. Now, these insurance companies, what they say is, if this earthquake occurs now, that is today actually, how many people are going to, how many deaths can be expected? They say that 90,000 people can be, expected, expected deaths are around 90,000. Now, if there is an earthquake in Kangra region, so the 20,000 people died during the Kangra earthquake. Now, this earthquake occurs now. In Himachal Pradesh, so now they say that expected deaths are something around 70,000, which is very huge actually. So this number. And then similarly, people have these insurance companies have also calculated, like how many expected deaths, as well as how many people are going to injury actually. Okay, because if there is now medical insurance is there, so they say that if there is going to be an earthquake in Assam of magnitude 8.1, they say the expected deaths will be something around 25 to 50,000, and the number of injury people will be somewhere around 50,000 to almost 1 lakh actually. So which means, the losses are going to be very huge if there is going to be earthquake right now. So this is basically due to industrialization, the population increase, you can attribute to several other rising, and growth of mega cities, and so many other issues are there. And now, I'm also showing you, this is also a very important slide. And now earthquakes means not only human loss, you also have an economic loss actually. So generally I used to present this slide, previously in many lectures also, but now I think this is now very relevant now due to this corona issue also. So like everybody is talking about the economic losses. So now earthquakes also can create huge economic loss. Now, if you see in 1950, there was a great earthquake in India that is magnitude 8.6. The economic loss was something around 5 million Indian rupees actually. And now if you compare this with our Indian budget, that is a 1950 Indian budget, which was the first Indian budget in Republic India. So the budget was something around 347 crores Indian rupees. So now if you compare this earthquake loss versus our Indian budget, it is, it's very small. It is something like less than maybe 0.01% of our total Indian budget. Now, if you see in 2001, Indian budget was $50 billion. And now 2001, if you see this Gujarat earthquakes, the economic loss was something around 5 billion, which is almost, 10% actually. So now, slowly earthquakes, the economic losses was very small in the olden days, but now, slowly, they have grown up and they have started challenging our, the economy itself. Now, if you see the Kashmir earthquake, which occurred in 2005, of course, it occurred in Pakistan, our Kashmir region also. The economic loss was reported something around to be $5.2 billion. Now, in 2008, China, there was an earthquake, some 7.8 magnitude. So the economic loss was reported to be $75 billion. And now in 2011, Japan, that is the Tohoku earthquake, they say the economic loss was something around $324 billion actually. And now if you just compare our Indian budget, so our budget is something around $382 billion. So now you can see if there is going to be a 9 magnitude or 8.5 magnitude in Himalaya, you can expect how much will be the economic loss. So these earthquakes also slowly, they have started growing the economic loss, and they have started, the economic losses are more or less they're challenging our the budget level itself. And now if you see this 2015 Nepal earthquake magnitude 7.8, so the economic loss was something around $10 billion in Nepal only, and almost 50% of Nepal GDP is consumed by this earthquake itself. They say that Nepal has become poorer by 50%. So this earthquakes means it's not only the human loss, the economic losses are also going to be, very high whenever there is going to be an earthquake actually. So here to just, like our Prime Minister, I think now all of you know how much is important of our economy due to this corona issues. Many salaries are being cut and followed. Right? So many issues are there. Like, so in earthquake engineering, so it is not only just the human loss. The duty of earthquake engineer has to protect the economy also. Both has to be done. Like, our honorable Prime Minister recently said before this lockdown, right? Jaan hai to jahan hai. Now that the slogan became, Jaan bhi, Jahan bhi actually. So which means, so we have to focus on human losses as well as, the economic losses also during this earthquakes. So now coming back to our seismic zone map, so I have shown you the importance of, this earthquake thing, human and economic losses itself. Now coming to our seismic zone map. So what's the problem with our existing zone map? So our zone map, what happens is our code gives you the PGA values like 0.1G, 0.16G, 0.24 and 0.36G. Now, if I ask you a question, say, like if I design for these values, are you safe actually? So, will you be safe? It's very difficult to you follow right, to answer this question actually, because in our structural design say, so the main objective is the safety. The structures have to be safe actually, but in where? So when you are building a new structure, say we expect that the structure will be safe in the future actually, in the next 50 years or something. And as all of future is a very, very dangerous word actually. Okay, all of now I think in this corona crisis, no need for me to explain the future. We never know what happens in the future. So it's a very dangerous word, and generally, we say that future is, uncertain actually. Okay, we don't know but past is also uncertain. But past appears as though deterministic kind of thing. They say it's like a randomness in disguise kind of thing. But future is completely, the uncertainty comes into picture actually. So now so the question, if you ask how much safe you are, then I say the code. Right now, the IS code doesn't provide any answer for this, uncertainty, anything for this quantification of this, the uncertainties. And now I will show you some, the maximum PGA value reported in our IS code is 0.36G, as all of you know. Now, this is the PGAs which has been recorded for 2011, Tohoku earthquake. Now, here, if you can see, the maximum PGA reported for this earthquake is something around 3G, the horizontal PGA. And now many stations near this, this is the epicenter. This is a star you can see here. And at many stations near the epicenter, the peak ground accelerations have exceeded gravity actually. So the PGAs are more than 1 times G. So now you can compare this number with our IS code. So our IS code, our maximum Z value is 0.36. But in design, you don't design for 0.36, you design for Z by 2. That is a point, 18G only you are designing. Now you compare your design value with this observed PGA value is almost, it is a 10 times, more than our IS code Z values. And now this figure is a very scary figure I am showing you here. So, as earthquakes are occurring, so instruments have come into picture. So people have recorded. So I have plotted here, this x-axis shows the year actually. So from 1930 to 2010, and the y-axis it shows the maximum horizontal PGA recorded till date actually. Okay, so if you plot this graph, so somewhere in 1930s when the first instruments started coming into picture, the maximum PGA was recorded was something around 0.2G actually. So at that time, people thought that earthquakes cannot produce PGAs more than 0.2 times G actually. Now suddenly in 1940 there was one earthquake, I think Imperial Valley around in US. Suddenly the PGA observed was something around 0.31 or 32 G actually. So now, so then so this record was maintained. This earthquakes never violated this PGA for 20 years or 25 years, and suddenly there was increase in the PGA value. Some 0.5G was observed during an earthquake. Then people thought that earthquakes can never produce PGAs more than 0.5G. And in 1971, so there was one San Fernando earthquake in US. Suddenly, the accelegrams, they have shown gravity. They have the recording shows that PGA can exceed 1 times gravity also. Then slowly, this record was this thing. And then finally in 2009, there was one earthquake in Japan where PGA was, report something around 2.6G was observed, was observed in the field. And now, if you see this 2011 Christchurch, New Zealand, there was one earthquake. Magnitude was very small. It is 6.3, but the PGA was recorded was 2.2 G. Then in Tohoku earthquakes also, as already I showed you, the PGA has exceeded the 2 times gravity at many locations in the epicenter. Now you can compare. Now, as already I told you, when you are designing the structure, say, you want the structure to be safe in the future actual. So now if I ask this graph, so like now we have plotted up to 2009. So this record is being held, and right now no earthquake has exceeded this one until date. So now if we see in the next 50 years, like in the 2070 or whatever, so whether the maximum PGS observed in the field will be 2.2 G or it will get exceeded, it's a very, very difficult question to answer. Now, similarly, I am showing you the vertical PGA also. Generally, we don't design for the vertical PGAs. Nobody designs, so everybody says only the horizontal component itself. But now, when you are constructing a tall buildings, cantilevers, or something, the vertical ground motion also plays a very important role. And generally, the assumption was the vertical things are not going to damage the structure. So this is the main assumption here. And now in our IS code also, so there is one formula that is, if you want to find out vertical PGA, it has to be taken as 2/3 times of the horizontal PGA, like the maximum Z value if it is 0.36 G, say. So 2 by 3 times is 0.36 G is this IS code recommended value. So this red line shows your IS code. And now here also I'm showing you the maximum PGS recorded as a function of year. So you see the from 1930 onwards until 1970 or 1975. So people thought that vertical PGS can never exceed some point is it 2 to 24 G or something like that. But suddenly, you see, as the data came into picture, so slowly people have found out that vertical PGS also could be high. And in the 6.8 Canadian earthquakes, the vertical PGA has been reported as something around 2.2 G. And now in 2009, this Japan earthquake, the magnitude was 6.9 only. The vertical PGA was observed almost 4 times gravity actually. So now, and now when you talk about future, say in the next 50 years or in the next 100 years, what will be the maximum vertical PGA will be same as 3.9 or it will be more. It's very difficult to answer actually. So these are the data is also showing like an increasing trend. So how much maximum PGA can be observed due to an earthquake? It's a very, very difficult, the question. People have tried to model by statistical approaches, but all are have failed actually. They were unable to predict, the maximum PGS at all. So now this is for the Christchurch earthquake 6.2. So you can see the axis is 1 times gravity is this units here, the horizontal and vertical. You can see at many stations, so this is HVAC station. So you can see the PGA is in the vertical PGA is almost, almost 2 times gravity, and it is more than the horizontal PGA. Like at this station HPSC, PRPC, the vertical PGA has exceeded gravity and it is much, much higher than using the horizontal things also. So now if we can compare this with our IS code, say our IS code, the maximum value is 0.36 G, but design value is Z by 2. So you are designing for this value. And now if I ask you once again the question, say whether you will be safe when you design as per the Z values, it's a very difficult to you follow, right? Answer these issues. So now, coming to our design problem, the problem, what we can say is, so as already I have shown you, earthquakes can occur on any fault and anything might happen in the future actually. So like, for example, let us take Ahmedabad city, which is in Gujarat. Ahmedabad is located here. So these red lines are all the faults actually surrounding your Ahmedabad city. And these are red dots. They show the epicenters of the past earthquakes which have occurred in Gujarat and this region. So now if you are designing an apartment, say in Ahmedabad city, so let us say its lifetime is 50 years. So now you want the structure to be safe in the next future 50 years, not in the past actually. Okay. So now when you see this one, so now, and you ask me, you see, what should be my design value? What should be the Z value to use for Ahmedabad? So now if we see in the next 50 years, any earthquake can occur on any fault actually. So like this marginal fault also can produce a 8 magnitude, or any magnitude also can occur, 8 magnitude or 7 magnitude, or anything is a possibility for in the next future 50 years. So now if you take all these combinations of possible magnitudes and distances for Ahmedabad city, you will get the maximum PGA as something around 4 times G or 3 times G actually. And minimum PGA, that means no earthquake occurs in the next 50 years, which means 0 G. So now your design value starts from, possible design value starts from 0 G to almost 3 times or 4 times gravity. Now, as all of you know, if you design for 4 times gravity or 3 times gravity, it's very difficult, and you see the walls becomes 3 times thicker or 4 times thicker, and the cost increases, and the space reduces. You follow. So it is a highly uneconomical kind of thing. Now, if you design for the lowest values, that is nothing but 0G, which means you are not doing anything. So which means you see your design will be economical, but it is completely, you follow, right, unsafe actually. So now we have to have a compromise between economy and then safety. So if you design for any value less than this maximum value, so that means you are taking a risk actually for this number itself. So now generally in the olden days, okay, so the design philosophy was like, it depends on the type of the structure. They say that nuclear reactors, historical monuments, they say that you can go for them depending on the importance of the structure, or the lifetime is higher, say. Like in nuclear reactor, generally, the lifetime or the return period is assumed to be 1 lakh years actually. So you design for the maximum PGA which you can observe in 1 lakh years times. And if it is an apartment or a building, so you can do for 50 years, like that, based on the lifetime of a building. So these numbers were decided. But now, after the insurance companies also have entered our this design, so nowadays the insurance companies, what they say is, you can design for any value you like. But so when you're not designing for the maximum value, if you're designing less than 4 times gravity, like 0.1G, 0.2G, or 0.3G, so these numbers will contain some risk actually. So now the insurance companies, what they say is, you cover your risk with insurance. So it is same as like us only. We all take life insurance policies itself. So life insurance policies, they decide a premium based on your age and then your health and other things. They take a decision. So here also, you can insure your building by taking insurance policy. So now the insurance policy person, they would like to know how much risk you have taken. They don't want your Z values, but they want how much risk, like whether you are taking 2% risk, 3% risk. So if you're designing for high value, say, so his risk will be very less. And if he's designing for low values, the risk will be more. So when risk is more, say, his insurance premium will be more actual. So this is a concept, which has entered our building codes also. Now, most of you, if you are taking a house in Chennai, or buying a house or anything, now banks are asking you to insure the house actually, because if something happens, and the EMIs doesn't get and the bank goes to loss, so the banks are also demanding that you take the insurance for your houses also. So now, so here, so the concept is so what we want is like this actually. So this is what I'm showing you, the seismic hazard curve for the Bombay city. That means, so for Bombay, so the design value lies anywhere from 0 to 0.8 G. So you can design for any value you like actually. But now your y-axis, it shows you the risk level, how much risk you are taking for these values. So like, for example, if you are taking 0.8 G, so the risk is something around 10 to the power of minus 5. So which means very, very low risk you are taking. Suppose if you design for 0.1 G, say, approximately, so you are 0.2 G, so approximately the risk level is 10 to the power of minus 3. So now the design philosophy is like this. You can take 0.2 G or you can take 0.8 G. And if you do insurance of your buildings, the insurance company, for a person who has designed for 0.8, his risk level is very small. So his insurance premium will be very small. But a fellow who has designed for 0.2 G, so his insurance since the risk level is slightly higher, the insurance premium also goes up. So this is a design philosophy now, which comes in our codes also. So nowadays, and this curve is very important for HVRA calculations and all other the issues. So nowadays, this is a thing which has come entered in all the building codes. And now, as all of this performance-based design, I also showed you in the introduction. So there also, they don't want, the one Z value. They want, some 4 or 5 Z values for variety of levels, like fully operational, life safety, and then the near collapse. And they have also defined, like the recurrence interval for a frequent means 43 years, occasional means 72 years, rare means 475, then very rare means 970. Then we have the same, that is a 2500 years. So now you have to provide Z values for all these recurrence intervals, and by this hazard curves you can get all these numbers actually. So if you can provide the seismic hazard curves, so people can do for to know, they will know the risk levels also, plus they can also do this the performance based seismic design also. And these curves are very important for vulnerability calculations, to find out economic losses, and other things also can be done with the help of these curves. So now this is what, the performance-based design is. That is how they define, like design earthquake maximum considered. So you have to provide for all these numbers. So now because these things are in great demand, so in 2009 actually we started working on to get these seismic hazard curves for all the cities in our India, so that this can be used in to prepare a new zone map also. Plus these values can be used for vulnerability, economic loss risk calculations also. So in 2009, there was a committee that is, which is most of them are from Bureau of Indian Standards. Professor CVR is also here. And so this report was brought out in 2011. And now this report, now as already I mentioned, we are revising this report. We have started from the last year. So now hopefully, you see, maybe in 1 or 2 years, the new these results will come into the public domain. So now I will show you this new, the results which you have obtained and the methodology to obtain the seismic hazard curves. So now I will not go into the detailed mathematics of this one. So if any of you know the probability theory, say, so in probability theory, there is one most important thing is the total probability theorem is there actually. So using this total probability theorem, so we define this seismic hazard. So we know that this ground motion that is here. So it depends on magnitude and depends on distance actually. So now we want to find out the risk associated with this ground motion. So now what we are interested is we want to find out all the PGAs from 0 to 4G, and we also want to quantify the uncertainty with all these numbers actually. So that is what is we are interested. That is what here I am in this equation. You can see this mu y star. It is nothing but the risk associated with these numbers. So now, as all of you know, this ground motion, say, it depends on magnitude, and it also depends on the distance from this the earthquake source. So to quantify uncertainty for ground motion, say, first of all you have to quantify uncertainty with magnitude as well as with the distance actually. So now from the total probability theorem, it can be written as a multiplication of three probabilities.
That is what here I am in this equation. You can see this mu y star. It is nothing but the risk associated with this
probability.
So now, as all of you know,
and the probability of distance, and this is the probability associated with this ground motion value. So by multiplying these three probabilities, we get this final, the risk associated with this numbers itself. So this approach is very widely available in textbooks also. You can see there is nothing, not great mathematics, just the total probability theorem we use actually. So now to find out this risk associated with ground motion, so now you have to find out, you see, the probability density function for magnitudes and distances also. That means you have to find out risk associated with this magnitude. That means, you see, what is the frequency of a 6 magnitude, frequency of 7, frequency of 8. So these have to be estimated first. So now among all the three probabilities, all are very well established. The only challenging thing is this magnitude itself. I will show you why. Now the main probability and the main difficulty in earthquakes is like this actually. So we all know that earthquakes are basically the plate tectonics is there, and this mantle cooling you would have studied in geology textbooks itself. Now here, if you see this whole process of earthquake generation, there are so many scales are the spatial and time scales are involved in this calculations. So like for example, the mantle convection, say, that means right, the mantle convection, like in the hot water when you boil something. So this mantle convection which arises from the core and it comes to the surface actually because of the temperature difference. So one cycle of mantle convection, the time period is around 50 million years to 200 million years actually. So just one cycle, you just imagine one cycle takes 50 million years, and this is what is driving the plates actually. And now our plate dimensions are so huge, like India means, you see, the Indian plate of 5,000, 6,000 kilometers. And I already showed you in my starting slide, the Indian plate velocity is something 5 centimeter per year. So most of the plates all over the world, so the plate's velocity is 5 centimeter per year, which is caused due to this mantle convection. Its time scale is, you see, 50 million years to 200 million years. And finally, when an earthquake happens, say like 7.8 magnitude earthquake, 90 centimeter gets released in few seconds actually. And why it releases in few seconds, I already told you the rupture speed is 2 to 3 kilometers per second, which is very fast actually. So like for 8.8 magnitude, say 400 centimeters gets released in few seconds in a small fault in the Indian plate itself. So now if you can see, our Indian plate velocity is 5 centimeter per year, and 8.8 magnitude is 400 centimeters in few seconds actually, or 90 centimeters per 7.8. So if you divide, say, so like 5 centimeter and 90 by 5, So you can see the Indian plate, if it has worked hard for 18 years of our Indian plate, this energy gets released in few seconds and in a very small zone in the plate itself. So you can see this earthquake is a very, very complex phenomena because of multiple time and spatial scales are involved. And then now we want to link this to our lifetime of our structures, like 50 years, 100 years, this 2,500 years. Things becomes very, very complicated, and there is no mechanics actual, no, like generally whenever in our structure analysis or this one, so everybody to start anything, so the first thing what to do is we write equation of motion. But now in earthquakes, say there is nothing like no mechanics model has been till date actually which can simulate these type of the large scales. So generally in earthquakes, you see, everybody does this empirical models also, that is this total probability theorem. Those things only we use it in practice. But earthquakes also show a nice phenomena. So like if you collect all the earthquakes which have occurred in all over the globe, say like from 1898 to 2012, and if you compare the frequency, it nicely, there are some 47 lakh earthquakes are there. If you see this number, say magnitude less than 5, there are 46 lakhs earthquakes are there, and greater than 5, say 75,000, 6 means 10,000, 1900, 92, 5 actually. So as magnitude increases, these numbers also decrease in a logarithmic fashion, that's exponential decay. So this is a famous law, what we call as Gutenberg-Richter law, which is widely used in earthquake engineering. That's a log 10 n is equal to the A minus side, the Bm. So where n is the frequency of the earthquakes and m is the magnitude. So now in our to compute the seismic hazard map of our country, say, okay. So now we have, these are the following steps. So the first step is identification of all the potential sources in our country. Then the estimation of the seismicity parameters. That means you see this AB value. That's a Gutenberg-Richter parameters for all these zones. And then the next step is this ground motion prediction equations. That is these are simple equations which give as a function of magnitude and distance the PGAs. And finally, you integrate all these things in the total probability theorem and get this, the seismic hazard curves. So these are the broad steps in, the seismic hazard analysis. And this is the first one. That is a listing of all the potential sources. Just 1 second. So now so the first step is identification of all these potential sources. So now so we have identified all the faults in our country. They are available in several reports, and from our official Geological Survey of India, they have given this map also. So it appears that there are something around 936 faults are there in our country. So total, if we include the faults from Tibet and from other sources also, it turns out to be total 940 faults, which can produce earthquakes, which can produce damage in our country. And now all these fault details are already available in the SEFI India website. We have given a KML file actually. Okay, so this KML file can be, if you click it, it opens in Google Earth, and you can easily see where these faults are located in our India, and your mobiles itself. You can try this file itself. And now coming to this earthquake catalog, now our India has a very rich history. Like we know, right, Ramayana, Mahabharata, we have a very huge collection of all these documents are there. And in our country, you see Mughals and the previous kings also, they all used to write their autobiographies, right, Akbar Nama, Babar Nama, Aini Akbari, many great documents used to be there. They are not only just autobiographies, but they all mention, what happened. They used to mention actually, like, at that time, how much money was spent and what happened, like when the earthquake happened, or, they used to write economic losses in these reports itself. So there are in India very, famous researchers are there, Professor Iyengar, then, Member-SS Bilham. They have worked extensively on these old documents, and they have, calculated all the years occurrence of these events and how much damage was there, and they have related to the magnitude. So all this old information is available online for our country. So now we have collected all these documents as a part of this seismic zone to build our seismic zone map. So these are, I'm listed here, the most important sources. One is this ISC GEM catalog. IMD, our Indian Meteorological Department, is official agency which reports all the earthquakes. Now that is online, anybody can see this data. Then USGS BARC, that is Baba Atomic, they also have their micro earthquakes and networks are there. And then Nepal, then several papers are there. So from all these things, we have compiled a catalog for our country. So total from the history onwards, if you see, there are something around 68,000 earthquakes have occurred in our Indian plate. And the main shocks, if you see, more than 8, some 26 events have occurred. So now this entire catalog also, I have put it in a KML format, and it is available in this SEFI India website, okay, which is you can download from this SEFI India. So if you click this the link, it will automatically opens in Google Earth, and you all of you can see nicely these epicenters. And if you click on any dots, it will show the year and magnitude and all other details. So you can download from SEFI India, and you can open in Google Earth itself. And now, so this is our the catalogs I have shown you, the faults I have shown you. Now the first thing is you have to do the declustering, that is removal of aftershocks and other things. So there are some classical the algorithms are there, Gardner, Nopov, many algorithms are there. Here I just wanted to point out that nowadays everybody is talking about machine learning, artificial intelligence, big data. So now these are emerging techniques, and you see, it will be very interesting actually to use. Nobody has done it, but to use these tools here to identify, to handle these type of the larger data sets, and identifying after foreshocks, which some of you can take it for as your research exercise. So now in our seismic zone map, we have used only the classical algorithms, also widely very well established for our the seismic zone map of India. And finally, so we have to do some statistical tests also, like completeness tests, because the data is not homogeneous and there are other issues are there. So all the things has been done, and the catalog is complete for the last 58 years only, because instruments came up only something around 1960. So the data we have is complete for last 58 years for magnitude, but as magnitude increases, say, so this interval also increases. So now after this seismicity parameters, after doing all the statistical tests, so we fit these type of recurrence relations. That is nothing but, the Gutenberg-Richter law. This is a truncated one. You can see here for all the source zones in our country. So total 33 are there. So these are our the recurrence relations. Now after this recurrence relations, say, okay. So the next step is this ground motion prediction relations. So now in India, here we have to do this gridded seismicity also. So now we have done one nice technique known as this elliptical smoothing technique, which is a combination of faults as well as the seismic activity. Like in India, the faults are known, but there are many faults are there which are not known, but earthquakes are occurring actually. So there is one technique known as elliptical smoothing, which can integrate these two epicenters and the faults to find out this activity rates also. So we have used, and these elliptically smoothened seismicity, we say. So these contours are the activity rates, we can say. So now you can see the activity rate is high, say. The meaning is, the earthquake occurrence is more in those regions. Like in here, if you see here in this Hindu Kush region, that is in the Pakistan, Afghanistan, this portion, the seismic activity rate is something around 0.1, which means you can expect more number of earthquakes in those places. Now in South India, say, activity rates are very small. So here the earthquake occurrences are very small kind of thing. Now in Himalaya, obviously, they will be high, and in Northeast India also they will be high. So now after doing this, the seismic activity, so now comes this ground motion prediction equations. So now there are several equations are there. A lot of data has come. Many researchers as well. Many international equations are there. So we have selected many of these equations to calculate our seismic hazard. And finally, so we use this logic tree kind of a framework to cater for the epistemic uncertainty also. And finally, we come up with this seismic hazard curve sector. So finally, the probability density function of magnitude has been worked out from the data. Then the location of the faults we know, that is from the elliptical smoothing, we have got these numbers also. And the ground motion relations also are there. Now we have to integrate all these three to come up with our seismic hazard maps. So now, as Professor Murthy also mentioned during his lecture on the first day, so now here in the new codes, they want to bring this performance-based design also. People can use, like not only giving values only for one set, we will give values for 73 years, 475, 2475, 5000 and 10,000 years also. And we also will give for mean value, m plus sigma, m plus 1.65 times the sigma, that is for the important structures. So we are going to provide values for all these, wherever I have put the ticks, so for all the contour maps for all these numbers. And we are going to give the contour maps for PGA, background velocity, displacement. So, and of course, the ratios we can find out actually. So now, when you move from mean to m plus sigma, say, for 2500 year return period, the values increases by 30%. And from mu plus sigma to mu plus 1.65 times sigma, we have observed that the values increase by using the 15% actual. Now, similarly for 475, these values are slightly, you see, on the higher side. So these are the contours actually. So now, so this is a 2,500 year return period, the contour map of PGA all over the country. So you can see the now, our PGA, that is Z value, you can see in the Himalayas and Northeast India, and even this value, you can see the values go from, you see, something around 0.3 to, you see, 1.2 G. We are also getting here. Now in the stable continental regions, the values lies from 0.1 to 0.2 G, except this Koina region where we will get very high values because of that Koina earthquake and others. And in Northeast India also we get very high values, something around, you see, 0.7 to 0.8 times G actually. Now here, the main advantage of these maps is, so now if a person is in Guwahati, he will design for 0.5 G. If a person is in Chennai, so he will design for some 0.12 G. Now the advantage is on the whole India, so although the Z values are different, but risk level is same actually. So the risk is 2,500 years, or 1 by 2,500 will give you the risk reciprocal of this return period. So now all over the India, risk level is same. So which means, you see, for insurance companies, the premium is, uniform for our entire country itself. But design values are different. So if you design for 0.12 G in Chennai, you are taking the same risk as in a person designing in Guwahati, but his design value is 0.5 G, but the risk levels are, you see, homogeneous. So this is what the advantage of, you see, these type of maps. Now in the existing IS code, we don't know how much risk we are taking for these numbers, but now in these maps, the main advantage is you can quantify. The risk is also specified when you're designing your value. So if you're designing a value of 0.5 G, means you are taking a risk of, you see, 1 by 2,500 years. So now I'm showing 95 percentile. So these, of course, these values will be very high because it is a mu plus 1.65 times a sigma. So these for 73 years, then 475 years, and these maps are very important for performance-based design. And of course, these values will be very high because they are, you see, the 95 percentile, not the mean values. And similarly, this is for 2,500 years. Then we have 5,000 years also, because now, the 5,000 years is required for when you're designing, you see, like you see the LNG plants, power plants, and other things. They say 5,000 year return period also has to be considered. So we are providing for 5,000 years also. And then this is your 10,000 years. So this is more very important for the nuclear power plants and very important structures. And of course, the design value will be very high, but the risk level will be, you see, very small actually. So you can see the values are more 2G, 1.7 G. See, we also get. Now you can compare these maps with, you see, the United States maps, which I showed in the starting. So now our numbers are also more or less similar to, you see, the other country numbers itself. And now this is for pseudo spectral acceleration at 0.2 seconds. So generally, if you see the international codes, they don't go by PGA kind of thing. They report what they call as, you see, short period coefficient. Then they also report, you see, this long period site coefficient, that is at 1 second also. So we are going to report for all the time periods, but I'm just showing here for 0.2 second at 73 years, then 475 years, and these are all 95 percentile values. So obviously, so they will be very extremely high. And this is at 2,500 years, and then this is for 5,000 years, and similarly say at 10,000 years also. So these are at 0.2 seconds. So this is also known as, you see, the short period coefficient. Now, in a similarly say, this is for 1 second. So generally, if you see international code, 1 second or 1.25 is known as what we call as, you see, the long period, the site coefficient. So these contours also I'm showing here. So, and these are also 95 percentile. That is mean plus, you see, 1.65 times, you see, a sigma. So you can see at 500 years in the Himalayas, this number turns out to be, you see, 0.3 times, you see, the gravity. Now, similarly, for 2475, 4975, and then you see the 10,000 years also. So we are providing you the values, and these values can be directly be used in the performance-based, you see, the seismic design. And now this is the more probable, you see, the seismic zone maps. Like we are discussing whether we have to give the values or whether we should go with this zone map. That is what is used, you see, the previously itself. So now so we have prepared some preliminary the seismic zone map here. So as we also divided it into some 4 zones kind of thing, like the existing the zone map itself, and these are the design values like zone A, zone B, zone C, and zone D. So the regions where the PGS are more than 0.6 G, say, if you map it in one color, so the zone map is looks like this. And zone C means 0.3 to 0.6 G, and zone B means 0.15 to 0.3, and zone A means 0.15 G. So you can see the Delhi, this Himalayas, and then this northeast, say, and even this Koina region, they show very, very high values from our seismic hazard. These are just a broad zone. This map has to be some more fine-tuned actually before it comes in our IS code, but just this is a tentative map because there are some small islands are here. They have to be modified. And when we change the zone maps, automatically some boundaries and other things are going to get changed. So, so these are proposed map, and this will get modified and it may come up in the future codes. And now, like Professor CVR mentioned, in the first day that you see earthquakes means is not force. It is basically the displacement kind of thing. So we have started working along this direction also. That is to construct these inputs for the required for displacement based design. That is this displacement is the response spectra. So now this is a peak ground displacement, the map for 475-year written periods. So now you can see the peak ground displacements in the Himalayas is something around 55-20 centimeters, whereas in the South India, these values are low, around 2 centimeter, 1.15, or of course in the Koina region we have a high value of 10 centimeters. Now, similarly, this is a 2,500 years, which is 2,500 written period. So obviously the values will be high. So now the displacements increases in active regions of 45 to 110. Then in our South India, say 1 to 10 centimeter, and in Northeast also is 20 to 60 centimeters have been observed. But all these values, the risk level is same actually. That is 1 by 2,500 years. And now these are the displacement response spectra. So we have constructed for various cities in our country. So most of you would have seen the pseudo spectral acceleration spectra, which is given in IS code. So these are the displacement response spectra, how they look like actually. So you can see this period where suddenly this straight line has two straight lines are there where this slope changes actually. So this you can see it is it varies with place to place. So like in India, say somewhere you can say 7 seconds, 8 seconds in the Ganga basin you can observe, whereas in the Himalayas and other places, say so this turns out to be somewhere around this in the 4 seconds. And now when we talk about energy, that is so energy is closely related to velocity. So we have done this peak ground velocity maps also. The values are of course something around 100 to 150 centimeter per second in the Himalayas, but when it comes to South India, say so 9 centimeter per second, or maybe 15 centimeter per second can be expected at 2,500 year written period. So now, so in our codes also, all our IS code also, most of you know that earthquake means it is only the horizontal things, spectral acceleration, velocity, and displacement. The vertical things generally are being ignored in the are not used in design actually. The code says 2/3 of this one. So now I will just show you some important things which we have arrived recently about the vertical response spectra also. So now I showed you this figure previously also, like this magnitude 6.2, this New Zealand earthquake. Where you see the vertical PGS was 2.2 times gravity, and they were more than the horizontal accelerations. So now what happens. So now this was observed in New Zealand. Now if you see in India also, say if we have now a lot of instruments have come up into picture. So if you collect all the data from observed for Indian earthquakes, and if you plot this V by H ratio, the graph you see looks like this actually. So this V by H ratio, it varies with the time period. It is not constant. Right now the IS code says 2/3 of this one, that is this blue line shows this IS code thing. But this V by H ratio you follow, right? It varies as a function of period, and they're very high actually. When you look at these data sets. And now when you do this, the hazard analysis for vertical GMP salts, that if you want to apply the vertical spectra, generally these values are slightly higher than what is recommended by this the IS code. So this matter also has to be looked into great detail, and maybe in the future codes this may also come up actually. And now it's not that vertical ground motion we are seeing today, but this is a very famous picture done by Dr. Oldham. Okay, he's regarded as a father of geological society. He established this GSI in India. So he observed in 1897 a great Assam earthquake. the boulders, they were dislodged actually. So they were overthrown into the air, and he has reported that the PGS, vertical PGS, was more than 1 times the gravity actually. So now how to design for this and how to account for this in design is a big a challenge nowadays. And not only this one, even we have done some numerical simulations actually for large magnitude earthquakes. We have also observed that this V by H ratios, say, they are extremely on the higher side actually, not a 2 by 3, and they are all functions of time period, and they will vary, they're more than our 2 by 3. And now, as Professor CVR mentioned, say, the code is in the code you will find out PGA, PGV, PGD only. But now there are some more extra parameters are there which indicates the damage. So generally PGA is not highly correlated with the damages nicely. So there are other things are there like energy-based design he mentioned also. So now maybe we are working on this RES intensity, other ground motion parameters, and how they link up with our design parameters also. So now to just have whatever I showed you, the seismic hazard thing. So all whatever I have shown you until now, it is available in your mobile phones. So everybody has Android mobile phones nowadays. So we have developed a small app that is the Seismic Hazard of India. So you can go to the Google Play Store. This app is available only in Google Play Store, but it is not available for iPhones actually right now. So if you go to Google Play Stores, if you type Seismic Hazard of India, so you will get this app. So anybody can download this app. Is free on Google Play Store. You can download in your mobile, and you can open this app. Say you will get all the design values, whatever I have told you, everything you can find out in this app itself. Like if you display catalog, if you click on any catalog, say, it tells you the latitude, longitude, then what date this earthquake has occurred, and what was the magnitude itself. And you can do many seismogenic zones. Everything can be plotted. Even the faults can be plotted in this app itself. So if you click on any faults, it tells you what type of fault it is, what is the name of the fault, and all the geological details also you can get from this app with just your finger touch. So you can just touch. We have given indicator also, and you can see the seismic zones also. You can 32 seismic zones are there. This app plots everything. You can plot these things in the app itself, and this opens in your Google Maps. And then we have also given these design values also. So if you touch any grid points, you will get what are the PGA values, for variety, I think like 475, 2475, 5000, and then 10,000 years. And even the spectral acceleration, then spectral acceleration at 0.2 as well as at 1 second. Now this app was done for A-type site in the world, and now the new values we are going to put up in this app so that all of you can use this. You can check the designs with these values. So now you can get even the design spectrum also. Right now we have linked it to IBC by using our long period and the short period coefficient, and you can get these spectra also. These are the response spectral accelerations for A-type site, B-type, C-type, the soil sites. All those things you can get from this the app itself at any point in the city in our India. And now for advanced users, say, our app also provides directly you can calculate base shear also. So if you give the natural frequency of your structures, some 6 natural frequency, whatever you want to do, automatically it gives you the story wise, the forces, and then finally it can give you the base shear also. So this option also is provided in the app. So you can use this app, and I request all of you to download this app and go through, once this app, which it is a very useful app. You will get all the design values. And now for advanced users also, we are going to release one more app. It is now in the beta stage, at the development stage. This app is very useful for people to compute SS, that's a site-specific spectra actually. Okay, you can do PSHA, DSHA calculations also using this app. See, most of you, nowadays the mobiles are, the very powerful mobiles are there. Like you see, the 4 GB, 6 GB RAM is there. So, the computation takes very little time in your mobile itself. Maybe 10 minutes or 5 minutes, you can get, the seismic hazard curve at any site you want by doing all these hazard calculations. So you can do this. This is what deterministic seismic hazard. You can plot 100 kilometer, 300 kilometer, what are the faults surrounding your site. You can get from this, and you can select a GMP, whichever you like, and you can choose a distance also, how much distance you want to include in your hazard analysis, and you can get the probability distribution function for magnitude, then the epicentral distance also, and finally you can get this. If you select say, from DSHA, like source to site distance, automatically it gives you the PGA also. This is for deterministic seismic hazard. Then finally, say you can get DSHA, and probability evaluations can be done. And finally, you can get this hazard curves also. Okay, so this app is for advanced users, and it works fine for the mobiles which has some 4 GB RAM or 6 GB RAM, and it's very useful to obtain this site-specific spectra. So we are going to release this app, maybe you see in another month or next month. This app is going to get released in the Google Play Store. So you can, if you click that, if you download the previous app, an update will be sent to you, and you can download this to compute your site-specific spectra also. So now I have shown you using this seismic hazard map and the current status and what you can expect in the future code itself. Now I will also show you some challenges, that is the near field ground motion, where you have to be extra cautious in designing the structures. So now generally the ground motion records can be classified into, you see, 3 types. One is the near source ground motion, we say. That means when the site is located very close to the faults, so like you are building in Himalayas, very close to the faults. So the ground motion using what we call as a near source ground motion. Then we have regional ground motion, that is far away, but not so far away, where vibration is the dominant. And then we have teleseismic, that is very, very far away, and we call this as a weak motion, and these are not of engineering interest. Now the whatever zone map, hazard analysis, whatever I have shown you, so that is perfectly valid for the regional ground motion. But when you are located very close to the fault, say, there are some special features, and you may have to take some extra care in designing these structures. So I'm just showing you one famous the earthquake, that is, I think earthquake in US. So you can see this is a fault actually. So you are having a station here. One is a Joshua Tree here. Then there is one more station here. Lucerne is here. So now you can see the earthquake, the epicenter was here, and rupture started from here, and it went through this direction towards this station, that is Lucerne. So now if you compare the two velocity time histories, you can see at Joshua Tree, the rupture is going away from the station. You can see the time history is only just vibration actual, and the velocity is around 43 centimeter per second. Whereas if you see this Lucerne station where the rupture is coming towards it, the velocities have suddenly increased, and it is no vibration. It is something like a long, the velocity pulse we say around that, and the velocity is also something around this 136 centimeter per second. So this phenomenon is known as directivity. That is a forward directivity, and this the backward directivity. That is a long duration we call as this one, and short duration we call as the forward directivity effects. Now similarly for Chichi earthquake, say, these features has been observed. These are the 3 acceleration time histories at TCU 52 station. This station is located almost on the top of the fault itself. So if you integrate acceleration, you get velocity, and if you integrate velocities, you will get displacement actually. So now the displacements are like this. You can clearly see here. So the displacement starts from 0, and it doesn't go back to 0. It goes to some permanent, you follow, right, this one. So this effect I showed you in my starting slides, the permanent ground residual displacement, or we call this as a fling actually in seismological terms. And you can see for Chichi earthquakes, the fling was almost 1 meter, and it is almost same as the peak ground displacement itself. Now this is for another station TCU is 68. Here also you can see this fling. So I'm just zooming the previous figure, so you can see. So this is what we call as a PGD, and this is a PGRD. So now when the station is very closely located to the fault cell, you will see this P ground residual displacement. When you are far away from the site, P ground residual displacement will be 0. Everything will come back to the original position. But when you are located very close to the fault or on the top of the fault, you will not come back to the position. You will go far away, so at some other location by 100 centimeters, or it may be there. It depends on the magnitude of your earthquake. Now these type of things have not only observed in the Taiwan, we have observed in Kathmandu, that is in 2015 Nepal earthquake. So at Kathmandu, say, these are the 3 accelerations. So there was instrument maintained by US people. So if you double integrate this acceleration, you will get the displacement. So you can see all the displacements, they don't go back to 0. So you can see a residual displacement of around 100, 200 centimeters in north, 100 centimeters in the horizontal, and also in the vertical direction. And now you can see these type of special spikes are the long period. You can see here. Generally, the response spectra will show one peak and goes here. But when you are in the near field, so you will see some special, other spikes around 4 hertz, 3 hertz also. You will see in this, the time histories. So now this is how it looks like. CVR also has shown this figure. So this is a famous bridge in Taiwan actually. So the most important thing was this bridge was constructed across the fault. So this is the fault. You can see here, this red line indicates the fault. So this bridge, this pier was on this side of the fault. This pier was on this side of the fault actually. Because of this permanent ground residual displacement, say. So you can see the piers, nothing happened to the piers, but the girder, you see, just collapsed actually. And the same figure, if you see from this side, so the same bridge, you can see there is a 7-meter waterfall has formed during this earthquake. And you can see the houses are all fine, the piers are all fine, only the girders have been collapsed actually. Okay, so now I have visited this Taiwan last year. So now what they have done there is, you see, they have repaired this bridge. The piers, they have not touched anything. Simply they have constructed the girder. Now previously the bridge was same level actually. Now you can see the ramp here. So the bridge is when you are going from this side, so it is something like slope is they have maintained, and this they have this bridge is in operating stages right now. And now this is also one famous bridge, Wuxi Bridge actually. Okay, so this was also crossing the fault. You can see here in the plan here. So now this bridge also during the earthquake, say, the fault has moved by 2 meters. You can see there is a permanent offset in this pier. So this here the damage was not due to the vibration, essentially due to the movement of the faults around by this 2 meters. Now this is also a famous dam, Shikang Dam in Taiwan. So this dam was also constructed on top of the fault. So now during this same Chichi earthquake, say, so this portion of the dam, you see, rose by something around 8 meters or 9 meters. So which led to the collapse of this dam. You can see the dam is perfect here. Only this portion, you see, because of this permanent offset, it just collapsed. So I visited this dam, the last year. You can see previously the dam was, the whole thing was here. This and now you can see this, it has raised by something around 8 to 9 meters actually, because this dam has been constructed on using the top of the fault. And now this is a track, CVR also has shown in his slides also. So there was a school, this running track was there in the school. So now what happened was during the earthquake, say, the fault was going below the school. So you can see this track was, there was a 2-meter uplift actually in this track. And now, the Taiwan, what they have done is all these things they have nicely documented, and they have converted this school into a, this museum kind of thing, the earthquake museum. So now I visited this museum itself. So you can see the fault scarp they have nicely preserved, which is people can see these near field issues. And now there is also one more school building during this China earthquake also. You can see here. So this building, these are 2 buildings actually. So this building is located on this side of the fault, whereas this building is located on this side of the fault. So during an earthquake, this portion has raised, and this portion came down. But luckily the buildings are safe. You can just imagine if the building was constructed across, say, automatically the structure could have collapsed due to this near source features. And now the near source features, say, they are very, of course, for buildings, you can slightly avoid these things. But if you want to build pipelines, railway lines, you have to cross the faults actually. So this figure shows the red lines are all, the faults which are in our country, and the blue ones, say, these are all, the oil pipelines in our country itself. So now you can see here, so these pipelines or railway lines have to cross these faults itself. Now how to design these things for this type of issues. So now this also Professor CVR also shown. This is a very famous pipeline in Alaska. So they all know that before designing the pipeline, they know that this pipeline has to cross this important fault, that's a Denali fault. So they have designed this pipeline for this near field ground motions also like this. So they have provided, this type of a slider beams where this pipeline can slide on them, and this resisted. And there was an earthquake, Alaska earthquake, some 7.2 magnitude earthquake, and rupture was also observed. And this pipeline, it worked nicely because of the slider beams. It just moved 14 feet horizontally and 2.5 feet vertically, and finally, this pipeline survived this the near field ground motions. So this is how we have to design, the structures near the faults or maybe crossing this faults. And this is also a famous dam in New Zealand. That's a Clyde Dam, we say. So this dam was also built on top of the fault actually. So they all know that if there is going to be a earthquake on this fault, so this dam is going to collapse. So what they have done is they have provided a joint here. So it is not like one dam; it is two dams actually. So which can take care of this, the permanent ground residual the displacement. So this is how they design the things which are located on top of the faults. And now this is one bridge which is crossing, the fault itself in Japan. So now here also, people have, so now this bridge is also crossing the fault. So now they have provided, an expanded, the bridge seat here, so that whenever there is a shift is there, so they can shift the track or, they can shift the girder or something. And you can see this box here. So this is provided basically, all the repair equipment is here. So if there is going to be any issues, they can quickly repair the things and make the railway. This is, I think, bullet train track. They can make the things work. So here the concept of resilience comes into picture. So how fast you can recover. So in the near field, you can't design anything. So at least if we cannot design, you provide this type of resilience thing, so that if a disaster happens, quickly you can repair the structure. And I have shown you some scary things, the near field ground motion, but the near field ground motion sometimes it creates some wonders also. So this is a beautiful lake in Northeast India. So many of you have visited. When I was working there, I also visited here. It's a famous Chandubi lake, which is located very near to Gauhati. So this lake was not there previously. So this lake was created by an earthquake. That is this 1897 earthquake. So you can see here in the Google map, there is one red line is here. So this map say, so you can see this red line here. So this red line indicates the fault here. So this, you can see this lake was formed very close to this fault. So this 1897 earthquake caused this earthquake, and now this lake is now a tourist spot. Many people, they go here, they take a boating, and they enjoy nicely the scenery. And this one was caused by earthquake itself. And there is one more lake, Palak Lake, which is in Mizoram. So there are several stories are there, like some snake was there and some things are there. But if you study all the historical documents, you can see that this lake was also produced by an earthquake in the past. So there was a village was there here. So this village, collapsed. They said that below this lake there is a huge village is there. So this village went down due to this this lake itself, due to this earthquake, and then this lake formed due to that. And there is one more famous lake in Tawang. So this lake was also created due to an earthquake. That's 1950 Great Assam. There is some discrepancies are there. Some people say that it was created due to 1950. Some people say there was one more earthquake in 1972. They have this earthquake due to this near field motion. So this lake was created here. There was no name for this lake actually. So now you can see here. So she is Madhuri Dixit here. So in, I think, Koila movie shooting happened here. One song was shot here. So since she performed a dance, so they call this lake in Northeast as Madhuri Lake actually. So on her name, there is one lake also is there. But this lake was created by an earthquake. And this lake is very beautiful and nice tourist spot in Northeast. And now I have shown you, you see, so this near field ground motion is very, very important. Now, if you see in Uttarakhand, in Himachal Pradesh also, they are building several dams actually, because to capture this hydro power. So many dams are built across, you see, on the top of the faults. And in Himalayas, there are several faults, and below the dams itself, many faults pass by, and some 1 kilometer, you have all these near source features itself. So now many of these dams are getting built in the Himalayas, and if there is going to be this type of near field sources, how these dams are going to behave or how the things are going to be, it's a very, very difficult situation. And now, but one good thing here is the near field ground motion. Now the thing is we can model it and we can simulate them in our computers itself. So there are analytical models are there where we can see this, we can simulate this the near field ground motions itself. I will just show some few things. So this was for the Nepal actually, which showed this near field ground motion itself. So now you can see in the Nepal, so the permanent ground residual display you can observe in Kathmandu city. You can see the city, you have seen large cracks. These cracks go up to kilometers because Kathmandu was located on top of the fault itself. And the data also shows this ground residual displacement. So now what we have done here is, these ground residual displacements you can model in computation. So the finite elements, these tools are able to predict exactly, how much these displacements will be like. So this is one finite element model for our entire, the Earth itself, which we did at our institute. So now these are some of the finite element meshes, where you can simulate earthquakes on large scales. So now softwares are there, and but only thing here is, if you want to do these type of large simulations, you can't do it on the ordinary desktops. You can run it in our supercomputers. So in our IIT Madras, we have a very nice supercomputer is there. But when it was installed, it was in the top 500. But I think this computer is old and new machines are coming into picture. So it has some 292 compute nodes. So we can run this type of large meshes for simulating earthquakes at large scales. And then we have done like so many, the models have been developed. Like this is for the Ganga basin also has been modeled here. And this is one small finite element mesh at a large scale, very fine in this Ganga basin region. And when you try to compare, say, so these models work very nice actually. They compare very nice with the data, and they're capable of simulating, this earthquakes itself. And this is for the Nepal. So you can see the red one is the recorded time history, and this blue one is, the simulated results. You can see the computation models are capable actually of matching the recorded data itself. And now this is one more model which is under so one PhD student is working on this problem for our South India to build this a huge finite element models to simulate these earthquakes. And because of lack of data set, we can use these computation models to generate these ground motions. You can see, so these are, so we have validated with this Gujarat earthquake, and many earthquake data sets are there, and these models work very nice actually in simulations. So now to just summarize my talk. So I have shown you the seismic hazard map of the India. So then I have shown you, the displacement, the response spectra. I have shown you even the PGV also. Then I have shown you this Android app also, where you can get all the details also. I request all of you, you can download this app and you can play with this app, and the new design values are going to come up in this app. So you try this app itself. And I have also shown you one more app which we are going to release maybe for advanced users to estimate the site specific spectra. So that also will be provided, so you people can use it and generate your site specific spectra. Then we have and I have also spoken about near field ground motion. Okay, so this is when you are located across the fault or top of the fault, you have to do something extra in your design apart from the codal provisions. You have to maybe provide some slider beams or maybe some joints actually when you are located on the top of the fault. So this is a very important thing, and there's a lot of scope for research in this area. Then I have also shown you how structures, if you build structures crossing faults, so what happens and how the international procedures are there. And then I have also shown you this high performance computing actually, which can be used for simulating, these earthquakes at a larger level. So you can generate, the data from these computational things, and you can use it in hazard calculations and other works also. Then now coming to the challenges, see like some of the students, if you want to do some PhD or research in this area, so now the burning topics are like how to do analysis and design of structures on top of the fault. So this, there are no codal provisions or codal guidelines actually how to do these things in our country itself. So some of you can take research in this area. Then other thing is urban earthquake engineering actually. So now generally all as an engineer, we are interested only in the structure actually, how this, when an earthquake happens, what happens to my structure. But nowadays we are talking about when the HVRA or hazard vulnerability risk maps, people are talking like how cities respond actually. Okay, that is resilience, all other things. So this also can be taken up as a research topic here. Then of course earthquake forecasting, say, okay, so nowadays earthquake is of course is the most popular problem, and nobody has been able to forecast earthquakes. But still, if somebody wants to do say something new things, one can contribute here. Then nowadays machine learning, so everybody is talking about the machine learning, artificial intelligence nowadays. So one can use this on our data sets actually. So nowadays instruments are put up, the whole world is highly instrumented, and earthquakes are occurring. Now I think the whole world, if you collect the ground motion, we have something around, you see, 2 lakh ground motion records. So now analyzing this 2 lakh ground motion records is very, very, complex actually. Okay, so there may be, and in future, if you see in the next 50 years, the ground motion records are going to be, you see, 10 lakhs or maybe 20 lakh records will be there. Now, how you are going to handle this amount of larger data sets actually? So here the machine learning, you see, everybody is talking. So these things also can be, tried actually. And not only on ground motion, even the earthquakes, that is aftershocks, how to find out. So these are some challenges. Some of you, if you are interested, so you can take up it in your research work. And these are the acknowledgements. So I acknowledge all the CED39, you see, the panel members who are, contributing to our seismic zone map. They are providing all the valuable inputs. Although I'm doing, but the inputs comes from them only. So, and we have to modify it actually once again, and maybe, by next 1 year or 2 years, this map may come in our IS codes. And of course, I also acknowledge NDMA, that's the National Disaster Management Authority, for the financial support, you see, to carry this project. And of course, whatever I have shown you here, the reports and the papers, whatever I have shown, all these things can be downloaded from my website, at the ResearchGate website. So all of you, if you just type in Google, you can go to my website. You can download the papers and you can see what research we are doing, and you can all the literature is available in my website. So thank you.